Hi, this is Markus Kasper of the European Southern Observatory, and I'm talking to you today about 30-meter telescopes. And these are slides I prepared with the help of the PIs of some ELT instruments, and also Susie Ramsay, who is in charge of ELT instrumentation at ESO. The overview of the talk will first introduce the motivation of why we're having big telescopes. And I'm talking about the extremely large telescope projects that exist. I will mention the first generation instruments for the European ELT. There's a MICADO Maori instrument, HARMONI, METIS. And finally, a few slides on the project that I mostly work on. It's not yet an existing project, but it's hopefully a second generation instrument, which is the planetary camera and spectrograph PCS. A short disclaimer, working at ESO, I have mostly slides about ESO projects, so this is a very Eurocentric presentation, but I want to mention that the US 30-meter telescopes are progressing on similar timescale with similar instruments, obviously. So for hundreds of years, we have now been using, or astronomers have been using mid-sized to large telescopes, the range of maybe a few tens of centimeters to a few meters. And since some decades now, we have the 8-meter class telescopes. So the VLT had first light, as far as I remember, in the late 90s, mid to late 90s. Currently, we are building the extremely large telescopes. This is going on at the moment. This will certainly be not the end of the road. There is a large number of potential other telescopes that could be built. We have some suggestions for names here in this list. Some are quite funny. You can have a look at them, but this is certainly something that will come in the future. On this slide, you see the primary mirrors of existing and telescopes and telescopes that are being built, and you can compare them in size. And for reference, down here, you see the size of a tennis court on the lower left and the size of a basketball court to the lower right. So the ELT is already exceeding the size of a basketball court, the ELT primary mirror. So quite impressive. But what you can also see on this plot here is that the biggest telescopes no longer have a monolithic circular aperture. They are made of all these small patches, so small mirror segments that are basically working together to mimic a big telescope mirror. And this is one of the key technologies actually that makes the building of large telescopes possible. So all these big telescopes are not anymore monolithic mirrors, but they are all made up out of individual small segments. And here on this plot on the right side, you see the temporal evolution with time of the telescope size from Galileo's telescopes in the early 17th century, starting at a few centimeters or centimeter size and going up to the 30, 40-meter telescopes that we are currently being built, building. And the reason for why we are pushing for bigger and bigger telescopes are actually threefold. The first one is the spatial resolving power, which increases with the size of the telescope. So the bigger the telescope, the smaller is the detail that you can resolve on the sky. Then you also increase the light gathering power. Simply a bigger mirror will collect more photons. It's proportional to the telescope aperture area. So d goes with d square. And finally, there is the imaging speed, so the time needed to reach a certain signal to noise ratio, which increases with the fourth power of the telescope diameter. I have a slide later to explain why that is. So all these advantages are realized and need a certain technology to be realized, which is adaptive optics. So only adaptive optics from the ground, when you look through the atmospheric turbulence, can recover the diffraction limited resolution of a telescope. And how the technology works in its simplest form is shown here on the left image. So you have the atmospheric turbulence disturbing the light wave. So you have a deformed light wave. It's not a plane wave anymore. This is entering the instrument, is analyzed by the wavefront sensor, how the deformation looks like. And then a real-time computer calculates the appropriate correction shape that you apply to a deformable mirror. And the appropriate shape is such that after reflection of the deformable mirror, you will have plane wavefronts and these will recover the diffraction limited imaging resolution only limited by telescope size. So on the right, you can see what adaptive optics, the effect of adaptive optics. So without adaptive optics limited by atmospheric turbulence, you would be observing a seeing disk, typically 1 arcsecond in diameter. And then once adaptive optics switched on, you recover the diffraction limited area disk of the telescope, which is much smaller, and you concentrate the light on a much smaller area. This simulation also shows the effect quite nicely. So on the left, you have the image of that's some cluster of stars here observed with the Hubble Space Telescope, which is 2.4 meters in diameter. Hubble Space Telescope obviously doesn't need adaptive optics because it's a space telescope. But still in the center, you have a bright blob of which you don't really know of what it is composed. Then when you have the bigger telescopes, you can actually start to resolve this blob into individual stars. And with ELT, with such a big 39-meter diameter aperture, you can see that the blob actually resolves in hundreds of stars. And you see much more detail in the image than you can see with a smaller aperture. Here's my slide on how I wanted to motivate this speed advantage of the big telescopes. So as we have heard before, the big telescopes collect more flux. It's proportional to the telescope aperture area, so it's proportional to d square. And then if you have adaptive optics, we have a diffraction limited point source image quality. This flux is concentrated onto a smaller patch on the sky because the area pattern linearly increases with telescope diameter, so the area decreases with telescope diameter square. And that means we concentrate more light into a smaller patch. And the effect is that, for example, the sky noise, which has a certain brightness per area on the sky, will stay constant in such an imaging scenario, because the flux increase by the bigger aperture is compensated by the patch size decrease. So the noise does not increase in the over the area pattern, and that means that the signal to noise ratio increases simply with the increase of the object flux, so which is proportional to d square. The noise stays constant. At the same time, signal to noise ratio for long observations also increase with the square root of exposure time. So when you rearrange this relation here, you can see that the time needed to reach a certain signal to noise ratio decreases with the 4th power of the telescope diameter. So that's a very important decrease. So the bigger the telescope, they are really much faster than smaller telescopes. As an example, a 40-meter telescope increases in speed at 5 to the power 4, so 625 times faster than an 8-meter class telescope. Yeah. And at the same time, the sensitivity increases by 5 squared, so 25, which in the near infrared brings you typically from a limiting magnitude of 23 in 1 hour to about 26.5 with the ELT. Sensitivity is not everything. So background limited sensitivity in for many science cases, you want to observe a faint object which is unfortunately located next to a bright object. So for that, you need high imaging contrast, and there is a paradigm. It's called high contrast imaging, which relies on 3 main pillars. It's a 3-step process. So first, you need an extreme adaptive optic system. Extreme means you have lots of degrees of freedom, and you run it very fast for a high correction quality. To produce an image which is very close to the area pattern with trail ratios of the order of 90% or so. Then the contrast is limited by the area rings, still of the order of 10 to the -3 to 10 to the -4, depending on the angular separation. But then you place the spot on a coronagraph, and the coronagraph then makes the area pattern goes away. So it acts like an optical filter that removes all the coherent light which is contained in the area pattern and leaves only the residual imperfections in the optical system, which are then typically at the level of 10 to the -5 or 10 to the -6. Then the image is analyzed by a scientific instrument, and depending on the nature, you can use you can exploit the differences between the stellar light and the planet light to further bring down the contrast. So, for example, if you have if you image with a spectrograph, you can use differences in the spectrum between the planet and the star. So this is called spectral differential imaging to identify the planet light. If you use a polarimeter, you can use the fact that the light reflected off the surface of a planet or from a circumstellar disk is polarized. So the degree of polarization is much higher than the one of the stellar light. And you can use that to differentiate as well. And finally, if you observe in a pupil stabilized image configuration where the field rotates, so when you track the sky, the field orientation on the sky changes with time, but the pupil orientation stays constant, then you can basically observe, or you can identify objects that rotate through the field of view while the optical imperfections stay in place. That's called angular differential imaging. With these methods, you can finally achieve imaging contrasts of 1 in a million or 1 in a billion, and that's what needed to observe the exoplanets or the disks. So now coming to the extremely large telescope projects, there are two major projects in the US. One is the 25-meter Giant Magellan telescope that is about to be built, or is currently under construction in Chile. It's on the southern hemisphere, in the Las Campanas Observatory. And there's a TMT that is most likely going to Mauna Kea on Hawaii, which is in the northern hemisphere. So here, these two projects provide access to the whole sky, northern and southern hemisphere, for the US community. ESO will only build a single telescope. It's called the ELT. You can see here an artist's impression how it will eventually look like. It will be sitting quite close to Paranal. You can see that here. So if you see this aerial view here, you consider you are the bird that has this view. The bird hovers over the Pacific coast and looks towards the east here. So you see Paranal and the Paranal base camp and Residencia. And about 23 kilometers in the back, in a straight line, there is Cerro Amazonas, which is the site where the ELT is currently being built. In the back, you see a volcano here. This one is close to 7,000 meters high. It's 200 meters away, 200 kilometers away. So it gives you also an impression how clean the air can be in the Atacama Desert. So it's really a great site, and it's impressive views from the mountaintops in all directions. This is a screenshot of the ELT site of yesterday. So the current situation of the ELT. See, there's still obviously a lot of work ahead. There's some concrete here already in this ring. This is a ring where the auxiliary buildings of the main telescope structure will be located on. The central area where the telescope will be sitting and rotating is just being prepared. The dome eventually will be a beast. It will be 80 meters high. It will have a diameter of 88 meters, more than 6,000 tons of rotating mass. And it will be a 30-minute walk from the entrance somewhere down here to the top of the dome. So it's actually really quite a hike, and it illustrates simply the size and the scale of this telescope. The structure is massive as well. It weighs well above 3,000 tons, and it's rotating on oil bearings, the biggest of which has 50 meters in diameter. And importantly for the instrumentation, the instruments will be sitting on Nasmyth platforms on both sides of the telescope. Each of these platforms has a size of 2 tennis courts stretched together. So it's about 15 times 30 meters, and they are 27 meters above the ground. The optics are interesting as well. So in contrast to current 8-meter telescope, which mostly have 3 mirrors, the ELT will have 5 mirrors. So apart from the main mirror, the segmented main mirror down here, there will be the secondary mirror as a convex monolithic mirror. And then there will be 3 mirrors located in the what is called the central tower of the telescope. So there is M3, which is again a concave monolithic mirror, and which reflects the light back to the M4 mirror, which is the deformable mirror. And that is a mirror that provides the AO correction and which will feed all the ELT instruments and will allow them to, with their internal wavefront sensor, correct for the atmospheric turbulence. And from M4, the light is reflected to M5. M5 is seen at a rather large inclination, so that's why it's elliptical and not round. It's a flat mirror. It's pretty lightweight, and it provides fast dip tilt correction and also the possibility to correct for telescope wind shake. And this tower here, you can see it's a big thing, and it has to tilt with the telescope when you observe close to the horizon up to about 70 degrees from zenith distance without introducing too much flexure. And so it's really a quite impressive and challenging thing to build. The primary mirror itself, you can see it here, consists of 800 hexagonal segments. Each of them is about 1.4 in diameter, and diameter means that from one corner to the opposite side. Then these segments are arranged in 6 identical sectors. So it's a hexagon, so there are 6 sectors which are all identical, and each host 133 segments, but each of these 133 segments is different. So you have 6 identical sectors with 133 different segments types each. And then there's another segment completely available that is used to replace, used for continuous replacement of segments. So it is foreseen for about to replace a segment each day with a newly coated one, and this process is continuously going on. In this case, the main mirror stays fresh and nicely coated over its lifetime. The blanks for the M1 segments are being made by Schott in Germany. They are cut polished by Safran Reosk in France, and the process of this preparing of blanks and polishing has already started and is going on, and is going still on for quite a while if you consider the number of segments that are needed. The main challenge of these, once you have the segments, is to put them together so that they act as a single mirror. And that means that you have to position them very, very precisely with an accuracy of about a few tens of nanometers. So that is 10,000 times smaller than the thickness of a human hair. So this is, as you can imagine, not a very simple task. So ESO is currently working actively on testing and developing the procedure of positioning the segments. And as you can see, there's a very complex mechanism that allows to bend and position the segments. And there's a small test facility being built where we stack together already a low number of segments. M2, M3 are the monolithic mirrors in the setup. They are about 4 meters in diameter each. It's worth noticing that the M2 is a convex mirror, so it's the largest convex mirror, outwards bending mirror that has ever been built. Both of them weigh about 3 tons, and they are mounted here in a fairly complex frame. In this frame, 3 tons of the mirror plus the frame is hanging 60 meters above the primary mirror in the telescope structure. So again, something that has not been done before. And when you think about it, well, I mean, it's a bit scary. Both mirrors will have silver coatings. It's important to notice the VLT had aluminum coatings, so silver has a higher reflectivity, and but will not provide easy access to the UV. M4 is mentioned before, is the deformable mirror. It's built by a consortium led by Adoptica in Italy, and the shells are built again by Safran Reosk. So shells means that this deformed mirror consists of a reference plate. The reference plate connects to the 5,352 voice coil actuators, and the voice coil actuators then deform the shell. And the shell is a 2 millimeter thick glass plate. In this case, it's split into 6 individual parts, which are produced separately. And then they can change the shape as fast as about 1 kilohertz. So polishing these shells is a very delicate task. They are fragile, And that's why there's a full set of spares. So instead of having just 2 or so thin shells spares, we have another set of 6 shells that could be used in case one of these shells breaks during the operation. Last but not least, M5 is the flat mirror that deflects the light towards a Nasmyth focus. And as I mentioned, it helps to correct for atmospheric turbulence tilt and also for wind shake. And it has a bandwidth of about a temporal bandwidth of 10 Hertz. So to achieve these kind of bandwidths with a rather large mirror, the mirror has to be extremely lightweight. So it's built of a silicon carbide structure. It just weighs 440 kilograms. So it is also a very, very challenging piece of technology. And finally, the last technology I want to mention here is the lasers for the adaptive optics laser guide stars. So in a nutshell, adaptive optics always needs a bright star near the astronomical target to measure the disturbance by the atmosphere. And because the guide star needs to be bright and close by, the sky coverage with natural guide stars is pretty low, only a few %. But you can create your own guide stars when you shine a laser of the appropriate wavelength into the sky. Then at 90 kilometers height, there is a layer of sodium atoms which absorb the light and re-emit the light. So the laser creates a small patch of light at 90 kilometers height. And this you can use for the adaptive optics. And this is a fairly well-established technology. You see here a picture, a real picture from the VLT, where there are already 4 such lasers in operation. And for the ELT, we consider a larger number. The baseline is 6 lasers, but potentially there could be also 8 lasers at a later stage. So now I will move from the telescope to the instrumentation suite of the ELT. And first of all, just to mention that all the ELT instruments will be on a Nasmyth platform. So the ELT will not have a Kasper platform or a Kasper focus below the main mirror. The Nasmyth platforms are huge. They are so huge that you could, in principle, even fit a 8-meter ELT on one of them. This is not what we're going to do, but it would in principle be possible. But it provides a lot of space for the instruments. And this is really needed because big telescopes need big instruments. It's one of the important things to realize, that the spatial scale in the focal plane is proportional to the focal length of the telescope. And the focal length typically is proportional to the diameter of the main mirror. So for the 39-meter ELT, it's 680 meters focal length. For the 8-meter VLT, it's 120. For the 4-meter entity, it's 38 meter. So that means that the focal plane, a patch on the sky in the focus of the telescope, increases with the telescope size. And here, to illustrate this, Jupiter with 40 arc seconds across would be 13 centimeters at the focus of the ELT. It would be 2 centimeters at the focus of the VLT and only 7 millimeters on the focus of the entity. So the focal planes are big, the relay optics are big, so that the consequence is that the instruments are very big. There's one exception. If you were simply to observe unresolved objects or a point source, a star on the sky, for example, take a high resolution spectrum, and you do that with adaptive optics, we have learned that the Airy pattern decrease in angular size with telescope diameter. So the diffraction limited spot size actually is independent of the telescope size, or roughly independent of the telescope size. So that means that if you only want to observe the diffraction limit, you can take a VLT instrument and put it on the ELT directly. It can be relatively small in this case. So these big instruments for the ELT are built by big instrument teams. You can see the 4 first-generation instrumentation teams, or let's say parts of them here. These are only a small subset of the number who are actually involved in these projects. And generally, ESO instruments are often built by teams from ESO community institutes and universities. Sometimes also ESO builds an instrument, but the first generation ELT instruments are all built by external consortia. ESO often participates in such teams to deliver some subsets of the instruments, for example, detectors or adaptive optics wavefront sensors, things like that. But ESO always follows up the development of the instrumentation with a team of engineers and scientists. So there are people at ESO working full-time on only the follow-up of these instrumentation projects. So how will the Nasmyth platform, this big Nasmyth platform, look in when the telescope is built? So here's a view that in the current expectation is that this would be the view of around 2028 of one Nasmyth platform with all the first generation instruments. So you have here in the front, that is MICADO. MICADO is fed by a multi-conjugate adaptive optics system called MAORI. Here, this thing on different platforms is HARMONI. And here in the back would be the METIS instrument. And MAORI provides a second port for another instrument that could be located then in this area, which is currently still empty. So a few more details on MICADO and MAORI. MICADO will start standalone. MAORI will need a bit more time, so it will start only with a single conjugate adaptive optics. And the instrument itself will be a versatile near-infrared imager and spectrograph. There's plenty of observing modes. You can do lots of things. It's a workhorse instrument. One science case is a precise measurement of motion of stars around the galactic center. I mean, something that gave the Nobel Prize this year to Reinhard Genzel and Andrea Ghez. And the Institute of Reinhard Genzel, the Max Planck Institute for Extraterrestrial Physics, is also the PI Institute of MICADO. MAORI is then will add another deformable mirror to the correction with M4, which is conjugate to a different height in the atmosphere. This will allow us to achieve AO correction over a larger field on the sky. So in 2028, when MAORI will be installed at the telescope, it will provide MICADO with a sharp images over a field of view of about 1 arc-minute. And it will use, MAORI will use laser guide stars, natural guide stars, and an additional deformable mirror, at least probably 2, which are located inside the structure here. So the observing modes that MICADO provides are imaging, astrometric imaging, high contrast imaging, spectroscopy. It does this over a large range of wavelengths in the near infrared. Field of view are up to 1 arc-minute. There's a fine pixel scale for the high contrast imaging with 18 arc seconds across. The requirement for astrometry is 50 micro arc seconds, which is quite impressive and will be challenging to achieve. The high contrast imaging requirements are a bit more relaxed, so these are not so difficult to achieve, and current instrument simulations already show that MICADO will exceed the specification as is listed here. The spectral resolution will be up to 20,000, and well, I mean, there's a simultaneous wavelength coverage of 2 bands, so either H to K band or Y to J band in one shot. So here you, on this short illustration, you see how the high contrast imaging mode of MICADO, what it will deliver. So on the left is an on-sky image of the HR 8799 star with 4 planets observed by sphere. Then this is simulated raw PSF that MICADO will provide. You can already see here that 2 of the planets appear in this raw image. And then they are here. And then in this simulation, 2 more planets were added at shorter angular separation and also more challenging contrasts. And also those were recovered, one at 10 AU with 700 Kelvin temperature, and the other one at 5 AU with a temperature that's similar to the ones of the others. So the brightness similar to the ones of the other here. And you can also start to see spectral features here. The 700K one, for example, goes away on the long end of the H band, so it has some methane absorption in its atmosphere, and that is something that you can also diagnose with a spectrum that MICADO will record. Finally, considering various error terms or errors that you expect in the instrument, you can start to predict what the performance curve will look like eventually, and you can compare it, in this case, for example, to sphere. So the sphere contrast, ultimate contrast that you can achieve is this purple dashed curve. The MICADO expectation is the blue curve here. And obviously, the main difference is that MICADO will push further in. So it will has a higher spatial resolution. It will go down to just a few tenths of milliarcseconds. And that is important because most exoplanets are sitting at small angular separations. And if you go for example, for the star-forming regions, the exoplanets, also the ice line, where we believe giant planets mostly form, is at an angular separation that is only acceptable in star-forming regions with the ELT, so at a few tenths of milliarcseconds. That would be the ice line in for example, in Taurus. The next instrument I wanted to briefly introduce is HARMONI. HARMONI is this two-floor structure that you can see here. It's an optical and near-infrared integral field spectrograph, also using adaptive optics. In this case, because the field of view is relatively small, it will use single conjugate adaptive optics, and the technology called laser tomography adaptive optics. So you use the lasers, but only to compensate for the cone effect. So it's still in one direction, using only M4 for the correction, and but having access to a large area, so it's basically a sky coverage, which is very large. The wavelength regime of HARMONI is extending into the optical. So it starts at about at visible wavelengths, 0.47 microns, to the K-band. So it's optical and near infrared. Spectral resolutions are between a few thousand and about 20,000 again. And well, the other interesting thing is that there are 4 different spatial scales, so 4 different cameras that produce different field of view sizes and pixel scales. And you can see them here. Here they are illustrated. They go from a large, almost seeing limited pixel scale of about 50 milliarcseconds size, down to a diffraction limited pixel scales with only 4 milliarcsecond pixel. And because of detector real estate available, you also need to consider the spectral dimension. You only have about 200 by 150 of these spatial pixels, 31,000 in total. And so with a 4 milliarcseconds pixel scale in the finest resolution, you have a field of view which is well below 1 arcsecond. So that's good for exoplanets, but it doesn't really give you the large picture of things. And that's why you have these other pixel scales. So depending on the size case, you can choose what you need. There are 3 spectral resolving powers in HARMONI, and it's always a trade between spectral resolution and spectral bandwidth that you can cover because of your limited amount of pixels that you have on the detector. So as you can see here, various gratings provide you either spectral resolutions of close to 20,000 over a very small spectral bandwidth, or spectral resolutions of a few thousand over 2 bands in one shot. So H and K band, for example, covered by this configuration here. HARMONI will also have a high contrast capability. So it will use the natural guide star mode with the smallest pixel scale and pupil tracking. And by doing that, you can create a high contrast image over a small area. And for that, HARMONI will not use a coronagraph. The main reasons are that coronagraphs need a precise pointing of the PSF onto the coronographic mask. And so they are challenging to operate. They make the optics a bit more complex because you need to relay also the DO plane and the image plane. So HARMONI chose a simple and very robust approach, which is the use of pupil plane apodisers only. And then in the focal plane, there are masks that will avoid that the central star saturates the detector and creates ghosts and so on. So these masks are transmissive to some part so that you can still see the central source for astrometry. But otherwise, the high contrast, the removal of the array pattern is achieved only by these pupil plane apodisers. And the performance goal is to reach a contrast of about 1 in a million at 100 milliarcseconds. So on this slide, you see the designs of these two shaped pupil masks. There are 2 flavors. One goes from 5 to 12 lambda over d. So that is the one that works at small angular separations between about 43 milliarc seconds and 100 milliarc seconds in H-band. And then there's another one that works from 7 to 40 lambda over d, so that gives you a larger field of view, but it doesn't go as much in. So it will provide the high contrast of a region from 60 milliarc seconds to about 340 milliarc seconds. And here you see the PSF contrast that this SP2 apodiser will achieve. So the raw PSF contrast goes down to about 10 to the minus 5. Then if you consider ADI, you can go further down to the required of, or to the goal of 10 to the minus 6. And you can take these instrument capabilities, you populate, you simulate a population of planets, and you see which planets you can recover. This exercise has been presented recently for HARMONI. And what you see is that planets down to about 1 AU orbital separation can be observed at about 30 parsecs for 20 mega-year-old stars. So the planet mass that you can reach at these orbital separations is about 3 Jupiters. So this is a ballpark figure for the planets that you can observe as HARMONI around nearby young stars. The contrast limit translates into about 10 to the minus 6 or 15 to 16 magnitude at such angular separations. You can see that there are more planets of lower mass down here, but they are at a fairly low SNR, signal to noise ratio. So you could maybe still reach them with a longer integration time, but this needs to be demonstrated. The last instrument of the first generation that I want to introduce is METIS. And METIS is a near to mid-infrared imager. So in contrast to the two previous instruments, it starts working in the L band at 3 microns, and then extends to the N band at around 10 microns. It provides imaging, low resolution spectroscopy, and coronagraphy. And for the 3 to 5 micron range, it has also an integral field unit. So like HARMONI has a small field of view that gives you spectral information and spatial information. Spectral resolutions in the long slit modes are a few hundred to a few thousand. In the IFU, the L&M IFU will have a spectral resolution of about 100,000, so very high spectral resolution. Field of view is relatively small, 10 arcsecond for the imager, smaller than 1 arcsecond for the IFU. And again, all observing modes will work with adaptive optics at the diffraction limit, which at 10 micron or the thermal IR is a bit easier to achieve than at shorter wavelengths. So here's a simulation of a disk observation with METIS, a model of a circumstellar disk here imaged in the CO line in the M band at 4.7 microns. So that is a model of the object. There is a small planet here with a circumplanetary disk inserted. You can see that depending on the radial velocities, on the spectral shift that you observe, you highlight certain areas on the disk, whether it's coming towards you or moving away from you. And then if you consider the METIS imaging performance, the IFU is here. And then you see the PSF. So this simulation is not using a coronagraph. You can see that METIS will be able to recover this circumplanetary disk in the CO line. It's a quite nice thing, a nice demonstration of the capabilities of METIS. Another important science case for METIS will be the observation of exoplanets. And here there is a prediction of the contrast that METIS is going to achieve with ring apodized vortex coronagraphs, and assuming various error terms, which are, well, I mean, they are reasonable assumptions. The important thing is that the contrast will be of the order of 10 to the minus 7 at 0.5 arcsecond, then about 10 to the minus 6 or so at 0.2 arcsecond. And this will be sufficient to start thinking about the observation of terrestrial Earth-like exoplanets around very nearby stars. So, for example, down here, you see a simulation for the case of Alpha Centauri A, where here there were 2 Earth-size planets put around Alpha Cen A at 0.5 AU and at 1 AU. And you can see that at 10 microns, you can detect both of those. The one at 0.5 AU is hotter because it's closer to the star, so it's brighter. But also the truly Earth-like planet in the habitable zone is recovered here with the METIS instrument. And at a shorter wavelength, at 5 microns, you only see the one that's further in, which is hotter. So you're at a shorter wavelength, you can detect it better. And the reason why you can observe terrestrial planets, you all know, I mean, such observations are extremely challenging, is illustrated in this plot here. You see the spectrum of solar system planets and the contrast to the sun. And there are always two bumps, characteristic two bumps. The one at short wavelength is in reflected light, where the star has its maximum and reflects light off the planetary surface. And then there's a second bump in the thermal infrared, which is because the planet itself has a temperature. It emits, it glows in the thermal IR, and that's where the sun already is reduced in the flux that it emits. So the contrast in this regime is favorable. It's more favorable by a factor of 100 to 1,000 compared to the shorter wavelengths. So that's one of the key advantages of the mid-infrared for such observations. Another it's not an advantage, but it's a feature that is illustrated here, is that in the mid-IR, of course, the optical depth is different. So you probe differently into the atmosphere of exoplanets, for example, you learn different things. So here in this picture taken of the same person in the optical and in the mid-IR, you can see that the optical, the light is reflected off the plastic bag, while in the mid-IR, you can look through it. And in the case of a planet, this plastic bag would be probably a high cloud layer, which you could not penetrate in the optical, but possibly in the mid-infrared. So, of course, the mid-IR has one big disadvantage when you want to observe exoplanets, and is that the spatial resolution is not very high. Even with the ELTs, you are limited to about 0.1 arcsecond separation. That means that if you want to observe Earth-like exoplanets in the habitable zone around nearby M stars, you will need to go to shorter wavelengths. And this is illustrated here by this plot. You see on the right side the synthetic population of planets, where you show the planet to star flux, where we show the planet to star flux ratio as a function of the angular separation. So, and the color of the dots indicates the spectral type of the star. So the red small M stars, which are numerous in the solar neighborhood, are up here. So their habitable zones are pretty close to the star because the stars are so faint. And that means that the angular resolution that is needed to resolve the planet from the star is a few tenths of milli-arcsecond only. And that is something you can only achieve even with the ELT at optical wavelengths. So it's a science case of the PCS instrument, the planetary camera and spectrograph. When you then move to the solar type stars, the contrasts become more and more demanding because the planet moves further away from the star, so it receives less light and the contrast goes down. And so, for example, for Alpha Centauri, which is a solar type star like the sun, the contrast is down to a few times 10 to the minus 10. And this is something that is probably exceeding the capabilities of ground-based instruments. That's where in the mid-IR, we have the very nice complementarity, because there with the contrast gain, we can still get to those planets. So in a nutshell, the terrestrial exoplanets around M stars are observed in the optical with PCS, and the ones around solar type stars are observed in the thermal infrared with METIS. And just to show how in the optical we plan to achieve these extremely high contrasts that are needed, not 10 to the minus 10, I said, was a bit below, beyond the capabilities, but still 10 to the minus 8 to 10 to the minus 9 is very challenging. And the way to achieve this is a combination of extreme adaptive optics with high resolution spectroscopy. So the extreme adaptive optics and the coronagraph bring you down into a PSF contrast of the order of 10 to the minus 5. And then you still need another 10 to the 4 contrast gain, and this is provided by the high dispersion spectroscopy. And this was already without AO demonstrated on Sky, that this is possible to find the one good planet photon in the sea of 10,000 bad stellar photons. And there are a number of validations of this concept currently going on with 8-meter class telescopes. Just to mention a few, there's HiRISE, there's KPIG, MECAOX, KEXEO. So this is really a hot topic and some important verification that is done at the moment. So I come now to my last slide. So these are simply the main takeaway messages from the presentation. So summarize it here. Ground-based ELTs with adaptive optics, they have a superb spatial resolution, proportional to the size of the telescope, and they gain more than 3 magnitudes in sensitivity and about a factor 500 in speed over 8-meter telescopes. So they will provide a huge push to the science you can do. The instruments for the ELT are extremely large as well. The imaging contrasts that you can expect with the first generation of the order of 10 to the minus 5 at 30 to 50 milliarc second separation, and approaching 10 to the minus 6 at 100 milliarc seconds and beyond. And that these kind of imaging performance is enough to think about observing giant planning forming at the ice line and star forming regions at 100 parsecs and probably even a bit beyond. So that's one very important science case that will be covered by MICADO and HARMONI instruments. Then finally, terrestrial exoplanets in the habitable zone are within reach of ELTs. I've shown the complementarity. In the mid-IR, you would do these observations for solar type stars with METIS, and in the optical near-infrared, you would do the observations of M stars with the PCS instrument, hopefully coming online about 2033 or 2035 in this range. And here on the right, simply see in the summary a typical parameter plot, wavelength and spectral resolution for the instruments that are considered for the ELT, the first generation instruments here, and PCS up here. And I come to the end of my talk and will now try to stop the recording. If I can. Here it is. Okay, goodbye.